using a program synthesis approach by Yanjun Wang from Purdue.
Yeah, thanks for the introduction. Today I'm going to introduce a program synthesis approach to learn network design objectives. This is a joint work with Chuanjiang, Xiaokangqiu, and Sanjay Rao. We are really excited that this work is accepted to HotNet this year, which is a prominent workshop in the network community. The network design problem can be very complicated. Given a network, there are plenty of source and destination pairs in the network, and for each source destination pair, there are multiple paths for each source to the destination. And given a set of demand, the network architect needs to figure out how to allocate resources to different traffics. A typical approach to solve this problem is to formulate an optimization problem with well-defined objectives. But sometimes it's not very easy for the network architect to trade off multiple objectives simultaneously, like the throughput, latency, or fairness of the network, etc. Here is a concrete trade-off problem that was addressed by Microsoft. The network architect wants to maximize the throughput while minimizing the latency. They managed to formulate a problem like this objective function. Maximize the allocation while with some sort of latency penalty that is controlled by a knob epsilon. Problem solved. But the trade-off between throughput and latency is not very intuitive. How to decide the knob is still like a black art to the network architects. It's pretty natural to think if we can generate those objective functions automatically. Since writing formal specifications is very challenging for average programmers, like the network architects, it makes sense to think if programming by example can help. The synthesizer only requires several input-output examples. However, given a network design scenario, it's very hard for the architect to provide a specific value or reward of the objective function. If the architect can provide such input-output examples, they may already know how the objective function would be like. But given a set of proposed network scenarios, the architect can provide a relative comparison between the scenarios. It's the same thing like if we are reading some papers. It's hard to give a specific score for each paper, but you have your own preference on those papers. The same thing happens here. The architect cannot provide a specific reward of the objective function, but he or she may prefer the latency of 100 milliseconds than 300. Then the question becomes that, can we synthesize objective functions given the preferences only? Based on the observation, we proposed a novel synthesis approach called comparative synthesis to generate objective functions. Given the function signature along with some domain knowledge, the comparative synthesizer can generate a set of different network designs and present them to the user. The user can rank those designs based on his or her preference and give the feedback to the synthesizer. The synthesizer can then leverage those preferences and generate another set of network designs. The user can rank them again. And the interaction will come to a convergence if there is only one function that can match the user's preferences. We then evaluate our comparative synthesis framework with a case study. In this case, the network architect cares about two metrics of the network, throughput and latency, and he or she may prefer satisfying scenarios. In other words, the network designs are more preferable if the throughput is greater than a threshold and the latency is less than a threshold. And the latency penalty should be different in satisfying and unsatisfying scenarios. Based on the domain knowledge, we can generalize the function template like this. Given the function template to the synthesizer, in each iteration, the synthesis task is to find two candidate functions and two different scenarios such that both the function honor the existing preferences, but these two functions have different preferences on the other two scenarios. If such two functions and scenarios can be found, the synthesizer will present those two scenarios to the user so that the user can state his or her preferences. If such two functions and scenarios cannot be found, which indicates that there is only one function that can satisfy the existing preferences, and it should be the solution. We developed a prototype of the framework and evaluate the framework on the case study. Turns out it works. The expected function can be synthesized in reasonable time and the number of iterations. Even when we tweak the target function a bit, the function can still be synthesized. And if more preference pairs are provided in each iteration, the solution can be found in even fewer iterations. To conclude, we proposed a novel synthesis framework called Comparative Synthesis to generate objective functions. And the preliminary result is very encouraging, but we still have a lot more questions to answer in the future. Can the synthesizer generate higher quality questions so that the number of iterations can be reduced? And can the synthesizer make better usage of the user's preference so that it can prove more search space in each iteration? And can the comparative synthesis be applied to more applications other than networking? And we hope we can answer those questions soon. And that comes to the end of my talk. Thanks.
So this is very cool stuff. And the question that I had when you first started presenting the talk seemed like it was answered, which is that anytime I'm thinking about doing preference ordering of different alternatives, a user might have circular preferences. They might not realize they have circular preferences, but they might at least express circular preferences. And if your synthesizer is only proposing pairs, you essentially are just going to stop. You can't create circular preferences because you stop as soon as you can't propose anything else. But if you're allowing people to propose multiple alternatives at each iteration, then I might give you a circular preference to begin with. What happens then?
I don't think people will provide circular preferences on network designs because throughput like 10 gigabytes per second must be better than 8 gigabytes per second.
But if I have a larger dimensional space, I could still see, I might not realize that I'm giving circular preferences. I might just not be thinking through all the possibilities, but it seems like it could still happen.
Yeah, I think the other direction we can explore is to develop some techniques that will make our framework more robust to the user inputs.
Other questions? Maybe you could say a little bit more about your future work, sort of what the next step is, or what the biggest challenges are.
The next step we are plan to do is to consider more a network matrix and make the framework more robust to the user input.